the principles that are going to underlay this issue of organic synthesis are going to be the same. Whether the question is scenario based, whether it is what, but organic synthesis is going to be tested in your organic chemistry. It is one of the major catchment areas. Why? Because it requires a lot of application. The application aspect in it is very key. In other words, from all the reactions that we are learning in organic chemistry, the organic synthesis is the part whereby you're going to be required to apply those reactions. And we are going to see the tricks. And some of the things I've learned them for a very long time. And I'm going to compress all the information that I have in organic synthesis and make sure that you guys are better students by the end of this 1 hour and 45 minutes. I'm advising you to please stay online until the end of the lesson. If you leave the lesson before it ends, you may not be in position to benefit 100%. Please make sure you stay online so that we all benefit from this information. Now, there are a few guidelines that I came up with that are going to be important for us when we are handling organic synthesis. Now, the first is that the first thing when you're handling organic synthesis, because synthesis has this kind of thing whereby you're moving from one compound. Let me say you're moving from compound A, and then you're going to move through a series of reactions to compound B. Now, the first thing that I'm saying here is that when you're doing organic synthesis, you must be in position to identify the target molecule clearly. In other words, the compound that you're synthesizing, you must be in position to identify it clearly. Make sure you understand the functional groups. Make sure you understand the functional groups that are present within the final product that you're forming, and then you understand how it differs from the starting compound. Then you go ahead and look for the reactions that are going to enable you to incorporate in those functional groups. So we are going to look at it practically, but this is just an overview of what you're supposed to have in mind when you're doing organic synthesis. You look at the final product, look at the starting product, look at how they are differing. For example, you're going to have a case like, I'm having some questions we are going to do, but let me just have some small example here. For example, I'm synthesizing this. I'm going to have this, and then from here, I'm moving to this compound. I'm moving to that compound. Now, if you're told to synthesize from chlorobenzene, you're moving to cyclohexanol. Now, the first thing I say that you have to be able to identify the end product very clearly, and then you're going to be able to identify the functional groups that are found there. The functional group that is found here is the hydroxyl functional group, meaning that this one is an alcohol. Then after, I am going to look at the beginning product that I'm having. The beginning product that I'm having is chlorobenzene. Now, what is the difference? That is the point that I stated here. You have to be able to let me look at the first point, to understand the functional groups that are present within the product that you're forming, and then you understand how it is going to differ from the compound that you are forming it from. And then you're going to look for the reactions that are going to incorporate it in. Now, when you look at this, you're going to realize that that here you're having the benzene ring, but in the final product, the benzene ring is actually absent. It is absent. That means that my synthesis is going to involve a step that is going to have a step that involves the removal of the pi electrons of the benzene ring. And then the step that aids the removal of the pi electrons in the benzene ring is actually an addition reaction that benzene undergoes. So I've been able to identify how I am going to be able to transform this chlorobenzene to cyclohexanol. Then I've also seen this hydroxyl functional group. When I look at that hydroxyl functional group, and then I'm looking at the carbon-chlorine bond. In that case, I'm going to see a way of transforming that. Now, the moment I look at that and I remember the reactions that we are given in organic chemistry, you're going to realize that this synthesis is going to be like this. You're going to move from chlorobenzene, you're going to move actually first of all to, you're going to move to phenol. So from chlorobenzene, you guys, there are people who are playing around with our screen. Now before we continue, now you guys first stop what you're doing. Before we continue, that pen-like structure that is found at your left, don't tamper with it. Do anything you want with your screen, but don't tamper with that pen-like structure. Now the person who has drawn the things here, you do the same thing that you did and make sure you remove them, because they are going to disorganize our screen. And the more you're making me keep on emphasizing this, the more it's going to become difficult for us to cover what we want. If you feel it is hard for you to listen and settle down, you just leave the lesson and go away, because nobody forced you to be here. So we are having chlorobenzene, and the most immediate compound I'm going to move to is phenol. So I will move to sodium phenoxide, and then after forming sodium phenoxide, I'm going to hydrolyze it to form ethanol, to form phenol. Then after forming phenol, I'm going to remove those pi electrons with the benzene ring, and then I'm going to form cyclohexanol. Then I'm going to form cyclohexanol. So we shall have something like that. Why is this disturbing me? Then you have that involved there. So in this case, the conditions of the reactions, let me just put it there. When you're moving to from chlorobenzene to phenol, the first step, we shall add sodium hydroxide. We shall use a temperature of 360 degrees Celsius at a pressure of 150 atmospheres. Then from sodium phenoxide to this, we shall hydrolyze that using a dilute acid. In this case, I will prefer dilute hydrochloric acid. Then from here, I will add hydrogen in the presence of nickel catalyst at 200 degrees Celsius. So I've been able to synthesize that compound. So our first rule, that is what it means. That is what our first rule means. You have to identify the target molecule clearly. Then you understand the functional groups that are present, and you see how they are differing from the starting compound, so that you go ahead and look for the reactions that can help you to incorporate in the differences that we are seeing. In the example, we saw that the final product was not having the benzene ring. Then the first product was having the benzene ring. It means that in my synthesis, I'm going to include the step that requires me to remove the pi electrons that are found on the benzene ring. So that is the first guideline that can be important when you're handling organic synthesis. Then you should also learn how to work backwards from the product. You should learn how to work backwards from the product. This is one of my best techniques. It is called retrosynthesis, to work backwards. Most of the times when you see the final product and you're not understanding how it can be derived from the first product clearly, most of the times what you do a retrosynthesis. You first move from the final product and you move a step behind. Now, when you move from the final product a step behind, you're going to realize that it is actually going to become more clear to you as to how you're going to be able to move from that final product to from the beginning product to the final product. Look at the first example that I gave, whereby I say that we are transforming chlorobenzene and we are transforming it all the way to that. Now, most of the times it can be hard for you to comprehend that, but if I'm using a retrosynthesis, I can move a step back from the final product. Now, when I move a step back from the final product, I am going to ask myself, from all the reactions that we have studied, how can we prepare this compound? And immediately I'm going to recall a reaction in which phenol undergoes an addition reaction. So I'm going to have phenol here, and then that phenol molecule is going to undergo an addition reaction such that this is OH. So we shall add hydrogen in the presence of nickel catalyst at a temperature of 200 degrees Celsius. So I have done a retrosynthesis. Now, after me doing that retrosynthesis, you're going to realize that it is now going to be easier for me to remember how I can synthesize phenol from chlorobenzene. It is going to be easier for me now to move from here up to phenol. It is one of the reactions that you looked at in the reactions of benzene or under the preparation of phenol. So you're going to see how easier it has become for you to solve that. In other words, to come up with the synthesis of that reaction. So that is the second thing that you should often do when you're doing synthesis. Learn how to work backwards from the final product. Then that will help you to consider the transformations that are needed to convert the starting product or the starting material into the desired product. So that is that. So we have looked at the first one, then we have looked at the second one. Now, for those of you who are actually here for the first time, before we look at the second thing, or before you leave the lesson, this is actually BIO-CHEM online clinic. We have actually had online holiday programs from the beginning of senior 5 first terms holidays, and the guys who are here, who have been around with us, can testify that their academic experience has not remained the same again. We still have about 40 slots for more students to enroll in. So please, after the lesson, you can contact me and I'll tell you the requirements that you need to enroll into our online program. But this program is a giveaway program. We want actually everybody in the country to be able to understand organic synthesis. So I believe we are going to have a very nice moment understanding these concepts. So that is the second thing that you should learn, to work backwards from the product. That is called a retrosynthesis. Then secondly, the next thing is that in the next guideline you have in organic synthesis is to use the reactions that you are expected to know. Use the reactions that you are expected to know. Now, for example, there are very many other reactions that are there in organic chemistry, but that is why I'm bringing for you that point. Now, whatever we are studying in A level it has what is called a scope. In other words, not everything that is in organic chemistry is going to be important for us at this level. That means that whenever we are doing organic synthesis, you should be in position to always use the reactions that you are expected to know as far as the confines of our A-level syllabus is concerned. So look at the reactions that are specified in our A-level syllabus. Don't just use anything just because you have come across it. Only use those reactions and those reagents. The reactions and those reagents from the A-level specification, and avoid very uncommon. Look at this point. Avoid using very uncommon reagents. Yes, they may be able to work, but because the person who is marking your work probably maybe that reagent is even not in the marking guide. So at the end of the day, you will lose marks. So what you do, make sure you train yourself so much to use the reactions that you have learned and that your teachers have taught you, and the reactions that are within the A-level textbooks. So that is the second point I would like us to know when we are doing organic synthesis. We are going to do some few examples. I told you I'm going to do 30 organic synthesis, and these 30 synthesis, I have prepared them in such a way that all the concepts that I am talking about are going to be domiciled therein. So that is the the third aspect. Let's look at the fourth aspect. The fourth aspect is that you should be in a position to choose appropriate reagents and conditions. This is a very important aspect when it comes to organic synthesis. Why? Because any alteration from the condition that is found within the textbooks means that the final product that you're coming up with is not going to be formed. For example, if I'm doing a dehydration reaction of alcohols, for example, I'm having this CH3, CH2, OH. Then after, I say I'm using concentrated sulfuric acid. You're seeing that? Now, instead of the known temperature range that we have of about 180 degrees Celsius, another student will say that, no, let me do it at 130 degrees Celsius. That alteration of that particular temperature is going to be able to cost you a lot. When you use a temperature of 130 degrees Celsius, you're not going to be in position to come up with the final product. You're seeing that? So always the reagents and the conditions that you have to use must be stated and written clearly. For example, there is heating. There are those conditions that involve heating. And then there are those conditions that involve warming. You should be in position to distinguish them very well. So when you're reading your organic synthesis, you can see a way of distinguishing them very well. See a way of mastering those reactions that involve heating and those that involve warming. For example, for me, what I did is that I actually decided, because the reactions that involve warming are actually very few, I decided to summarize all the reactions that involve warming in organic chemistry. Then it means that the rest of the reactions, apart from those ones, involved heating. That is how I was able to master that very well, and most of the times I had correct conditions. For example, you also have a condition where you may be required to use a concentrated acid. There are also those conditions where you're required to use a dilute acid. For example, a nucleophilic addition reaction of these carbonyl compounds, where they react with potassium cyanide in the presence of dilute sulfuric acid. It is not concentrated sulfuric acid. So any alteration in that particular condition is going to cost you a lot in your organic synthesis. Then you're going to have aqueous or alcoholic solutions. All those are going to come into play, because the use of an incorrect reagent and the condition means that the final product will not be formed. Okay, consider the reaction conditions carefully. For example, temperature. There are those reactions that take place within a particular temperature range. For example, we looked at this dehydration reaction, where you're having an alcohol reacting with concentrated sulfuric acid at exactly 180 degrees Celsius. But again, there are those reactions that just involve heating. In other words, they do not have a specific temperature requirement. So you should be able to distinguish between those reactions. You should be able to look at those reactions that have catalysts. You're seeing that. And then you also should take note of when you're required to warm and to heat, and when you are supposed to use specific temperature conditions. So that is point number 5. We are done with point number 4. We are going to look at practical examples that are going to be involved in that are going to show us exactly how we are going to use these keys that I've given you. Then number 6 is one of the most important. If you are dosing, wake up. Number 6 is one of the most important. Most of the times when you are doing organic synthesis, you should be in position to account for the changes within the carbon length or the carbon content that takes place between the final product and your beginning product. That means that there are some reactions that require you to add the number of carbon atoms. So you should take note of all the organic reactions that make me to be in position to add the number of carbon atoms. I'm going to summarize them here for you, and your work is only going to be to read through. Then you're going to have those reactions that are going to you're going to have those syntheses that are going to require you to reduce the number of carbon atoms. So for example, the beginning product has 3 carbon atoms, and then the final product has how many carbon atoms? Has 2 carbon atoms. That means that in your synthesis, you're going to be required to include a step that requires you to reduce the number of carbon atoms by 1. And then some may require you to rearrange. This one is a little bit complex. Some may require you to rearrange the carbon atoms. So the point is here. You should be in position to know. You should be in position to have those particular reactions that can increase the carbon chain, increase the level of branching within the carbon chain, and also reduce the carbon chain. This is going to be very important for us when we are handling organic synthesis. And I'm going to summarize all of them. I'm going to summarize all of them. I'm going to summarize all of them in this particular lesson. So you're going to realize how organic synthesis is going to become very easy for you. So that is number 6. Be able to account for the carbon chain length changes that take place in your synthesis. Then number 7 is avoid impossible reactions. There are reactions that do not exist. But because because you want to write in something, you're just going to just get any reaction and put. For example, you cannot oxidize an alkane. So somebody can say maybe CH3. Let me use a brighter ink. Somebody can say CH3, CH2, CH3. Then maybe the person wants to oxidize this. And the person is in an exam and you want to oxidize that. This reaction is impossible. It is not there. Alkanes cannot undergo oxidation reactions. So always avoid impossible reactions in your organic synthesis. Avoid impossible reactions in your organic synthesis. What does that call for? That calls for a particular level of mastery that you're supposed to have when you're handling organic, that when you're reading your organic chemistry. Why? Because reading organic chemistry involves you knowing all the reactions that are feasible within your scope, and then you should be able to use those reactions in an appropriate manner to come up with the final products. So always make sure that your reactions are chemically feasible as far as the A-level scope of the syllabus requires. Then number 8, check on the final structure carefully. Make sure that the final molecule has the correct. Make sure that the final molecule that you are the final molecule that you have come up with has the correct functional group. In other words, the carbon chain, the carbon skeleton, and the number of carbon atoms. Then after, so this one here is okay. Then there's also another important thing that you must consider here. Number 9. Whenever you're doing organic synthesis, ensure that you keep the roots as short as possible. Whenever you're thinking from all the reactions that you have studied in organic chemistry, make sure you be able to keep the roots as short as possible. Examiners usually prefer efficient synthesis that have a minimum number of steps, because the fewer the steps, the more efficient and even cheaper it is for you to carry out the synthesis. So from all the reactions that you're going to be thinking of as you're doing organic synthesis, you should be in position to use those reactions that are going to give you the least number of steps. And most of the times, preferably, you're supposed to use about 60 steps. However, when the worst comes to the worst, you can go to about 7 steps. But you have to think and see a way of condensing those steps into about 60 steps. So that is also one of the things that is tested in organic chemistry. From all the things you're going to be able to learn, we are going to test your ability to be able to filter that content and compress it so that you have efficient synthesis. So those are the guidelines that I came up with and so important for us when we are handling organic synthesis. Those are the steps. So I'm going to look at the next thing that I'm calling the secret weapon. The secret weapon. The secret weapon. For those of you that have not yet enrolled for our online program, please make sure you do so. If you're not in any of our WhatsApp platforms, you can be in position to get my contact or for our admin. So admin desire, make sure you can put our contacts in the chat so that people are able to see. Have those contacts in the chat so that people are able to see. Now, January is going to be a blast. We are going to do a lot of work in January. For those of you who are doing biology, we are going to do the last topics of biology: evolution, genetics, mechanisms of speciation, and all those topics. It is going to be fun. If you have not yet enrolled, make sure you do so before the year ends, because we don't want you to miss out in any way just because of ignorance. So that is that. Now I'm going to look at the secret weapon. The secret weapon. I'm going to look at them one by one, and I want you guys to pay maximum attention. Please make sure you pay maximum attention. I'm going to look at these secret weapons. Why? Because you may not find any book that has, now these are the reactions that increase on the carbon chain. These are the reactions that do this and this. No. What I did is that I sat down, and because of the need to simplify organic chemistry, I came up with a few some reactions, and then I ended up classifying some of those reactions into clusters that are in position to help us understand the things better. So I'm going to look at them one by one, and they're really going to drag a lot of time. So I want people to be patient, and at least, even if we don't do the numbers because of time, make sure that you grasp the secret weapon. I'm going to look at those reactions that increase on the carbon chain. I'm going to summarize all of them. I'm going to look at those reactions that decrease on the carbon chain. I'm going to look at those reactions that involve the use of reducing agents, those reactions that involve the use of oxidizing agents. Then I'm going to look at the reactions that involve the manipulation of the substituent groups that are found on the benzene ring. Then I'm going to look at the reactions that have specific temperature conditions and those that do not have general temperature conditions. Now, by the end of this, you're going to learn how to read organic chemistry, and it is going to be fun. By the end of January, you guys are going to have a good time with this organic chemistry. Before us continuing, there is that pen-like structure that is on the left of your screen. What you do, instead of you can do any other thing on your screen, but do not play with that pen-like structure, and do not dare to write using that pen-like structure. Why? Because it is going to affect my display that I'm having here. So when you're writing on your screen, you'll also be writing on my screen at the same time. So make sure you avoid that, and so that we move on very well. So I hope the admin has actually put the contacts in the chat, and you shall be in position to see them very well. Okay, so we can proceed, and I'm going to look at the secret weapon. Make sure you listen carefully, and the moment you get this, you're going to master the whole of organic chemistry, and you're going to tame it like a puppet. Wherever you call it, it will obey you and it will follow you for the rest of your life. So let me look at the secret weapon, and so we are going to start by summarizing the reactions that increase on the carbon chain. So these are the numbers we are going to do. I made sure I compiled them myself. I chose the best of the best that can be in position to show us the information that I'm trying to talk about. The first thing I'm going to look at is going to be the reactions that increase on the carbon chain. The reactions that increase on the carbon chain. the reactions that increase on the carbon chain. This is very important in organic chemistry. Once you know all these reactions that enable us to increase on the carbon chain, it is going to help us to do the organic chemistry very easily, very easily. But before that, for those of you that want to enroll, so if at all you choose to enroll today or any other time, you're going to have access to what is called our Google Drive. And our Google Drive has all the recorded lessons ever since I began teaching this third term holiday, such that you also keep in pace with other students and you don't miss out on this big opportunity. So the first one, the first reaction that we have that is going to be enable us to increase on the carbon chain is going to be the nucleophilic substitution with cyanide. That is the first reaction, whereby you're going to have an alkyl halide. It's going to be a nucleophilic substitution reaction of alkyl halides. A nucleophilic substitution reaction of alkyl halides. Make sure you don't leave this lesson before the end, because this lesson I'm actually going to show you people the tricks that I've learned for a very long time. And the moment you're able to master them, you're going to be able to tame organic chemistry like a puppet. But the advantage is going to come from your ability to be in position to stay until the end of the lesson. I don't want people to get half information. So our contacts are on the chat. You can be able to get them and follow up on the online program. Now, the nucleophilic substitution reaction of alkyl halides enables us to increase on the carbon chain. Now, this nucleophilic substitution, we are substituting it with cyanide. Cyanide, and cyanide is like that. So you're going to have an alkyl halide. For example, you're going to have CH3. Now, you guys who are writing on our screen, I don't know, but you guys are really making us, you're really giving us hard time. Eh? I've said again and again that don't touch on that pen-like structure that is found at your left, the left part of your screen. Now, if the screen is very small for you, the advice that you do is that when your phone is on portrait mode, the screen is in the middle and you may not be in position to see very well. What you do, you rotate your phone such that the phone is on landscape mode. In that way, the screen can be very large and you can be in position to see it clearly. Okay, let me minimize my screen if that is the issue. Let me minimize my screen if that is the issue. I hope you guys are seeing it very well. But only one person complaining. I don't know. Is it a general problem? Are you guys in position to see my screen, my screen freely? Are you guys in position to see my screen very well? Because I'm seeing only one person is complaining. Minimize the screen, minimize the screen. Now make sure you're having your summary books so that you're in position to summarize all these reactions. And we are going to look at the practicality later on when as we are doing these other numbers. Okay. So the first reaction is the nucleophilic substitution reaction of alkyl halides. For example, you have an alkyl halide of this nature. You have an alkyl halide of that nature. CH3, CH2, Cl. Now, in case I want to increase on the carbon chain, in case I want to increase on the carbon chain, what I do is that you're going to add this. But this reaction is one of the nucleophilic substitution reactions of alkyl halides that we looked at. So you're going to add potassium cyanide. You're seeing that? in the presence of ethanol, in the presence of ethanol, and then you heat. What is going to happen is that the halogen atom on the alkyl halide is going to be substituted with the cyanide molecule. So you shall have CH3, CH2, Cn. So in this way, you have increased the carbon chain by one carbon atom. So you have increased the carbon chain by one. That is the first reaction. Then from here, from this ethane nitrile, that is the name of the compound. This is ethane nitrile. What you can do is that this reaction can lead you to form a carboxylic acid. In other words, we looked at that under the preparation of carboxylic acids. For those of you that are part of our holiday program. So we can prepare carboxylic acid of CH3, CH2, COO, OOH. In that way, what did we say when we are doing that? We use acidified water and then we heat or reflux. Acidified water and then we reflux. So that one is going to give us a carboxylic acid. And then from this carboxylic acid, you can have many other organic reactions that you can go to. For example, you can go to an alcohol. You're seeing that? And then the other reactions come in and the synthesis can continue going on up to about 1,000 steps. So that is the first one. A nucleophilic substitution reaction of alkyl halides. Then the second one, make sure you summarize that. The second one we have is the addition of hydrocyanic acid to aldehydes and ketones. Addition of hydrocyanic acid to aldehydes addition of hydrocyanic acid to aldehydes and ketones. This reaction, we looked at it when we were looking at carbonyl compounds, where we looked at the nucleophilic addition reaction of carbonyl compounds. So in this case, we shall have a carbonyl compound, CH3, C double bond O, CH3. We say that hydrocyanic acid cannot be obtained directly, but rather it is prepared in situ. So we shall have potassium cyanide here as the condition in the presence of dilute sulfuric acid between a temperature of 10 to 20 degrees. Now, when I was looking at my guideline, I said that these conditions and the temperature conditions are supposed to be mastered. In other words, you're supposed to cram them the way they are. Any alteration to this is going to give you a wrong answer. So what is going to happen? We shall form that CH3C, shall have OH there, then I will have Cn, then I will have CH3. In this case, the carbon chain has increased by 1. So we have added that carbon atom. Now, Enoch, it looks like you're having maybe a personal problem because the rest of the students have confirmed that they are okay. So I don't know, try to fix your screen very well. So in this case, we have increased the carbon chain. Now, because we are having a cyanide group there, we can convert this to a carboxylic acid. How? By using the same condition. Remember here, when we're converting this to a carboxylic acid, we used acidified water and then we refluxed. To reflux means heating for a long period of time. So this part is going to be converted into a carbonyl, into a carboxyl group. So we shall have CH3, C, OH, CH3, then I'll have C, OO, OOH. In that way, have been in position to increase on the carbon on the carbon chain. For those of you that have been with us, you looked at that reaction. It increases on the carbon chain. It was one of the nucleophilic addition reactions of alkyl halides that we looked at. Then we are going to look at the next one. I'm going to summarize all of them. I'm going to summarize all of them. So I'm actually making your work very easy. The next one is going to be the Grignard reaction with carbonyl compounds, whereby the Grignard reagent reacts with carbonyl compounds. The Grignard's reagent reacts with carbonyl compounds. So I'm going to say the Grignard reaction of carbonyl compounds. Of carbonyl compounds. Now, this reaction, we looked at it under the preparation of alcohols. It is one of the reactions we looked at. And this reaction is important because it also increases on the carbon chain. So we are going to see how it happens. So whenever we are having we looked at this reaction under the preparation of alcohols. So you're having that carbonyl compound. Then we say that this can be converted to an alcohol, but you're going to add a Grignard reagent. But what is a Grignard reagent? Somebody wanted to take a screenshot of that. Please do so very fast. A Grignard reagent is an alkyl magnesium halide. In other words, you're going to have an alkyl group, a magnesium atom, and a halogen atom. So in this case, you're going to add a Grignard reagent. So which Grignard reagent can we add? I can consider any, depending on the number of carbon atoms that you want. So I can have CH3. Let me just consider one, CH3 MgBr in the presence of dry ether. So after me having that, you're going to realize that this is going to add itself there. So I'll have CH3C, then I'll have O, MgBr, then I'll have CH3, then I'll have CH3. Then after, I'm going to hydrolyze that. I'm going to hydrolyze that using a dilute acid. I'm going to hydrolyze that using a dilute acid, so I can say this is dilute hydrochloric acid. So I'll form CH3, C, O, H, then CH3, then CH3. So you would have done the Grignard's reaction of these carbonyl compounds. So that one is also important in helping us to increase the carbon chain by any number. So the number of carbon atoms that you're going to prefer to increase the carbon chain is going to be dependent on the length of your Grignard's reagent. So the length of your Grignard's reagent is going to be able to dictate that. Now here, because we are forming a secondary alcohol, we are not going to use a dilute acid. Rather, we are going to use aqueous ammonium chloride is what we use for hydrolyzing. That is going to form a tertiary alcohol, sorry. So I'll have aqueous ammonium chloride in its aqueous state. For example, another example, I can have this where I'm having CH3C. Oh, this is an aldehyde. Then I'm going to add a Grignard's reagent, methyl magnesium bromide in the presence of dry ether. So I'll have CH3 C. Then I will have O, Mg, Br. I will have my H there. Then I will have my CH, my CH3. Then I hydrolyze it using an acid, a dilute acid. So in this case, I may have dilute hydrochloric acid. So I'll have CH3, CH, OH there, then CH, CH3. And I would have formed a secondary alcohol. Now this reaction, note that this reaction can help us to increase the carbon chain by any length. Then it's also one of the reactions that can be used. Let me even write it on red. It can be used to move through, let me use that word, to move through different classes of alcohols. Through different classes of alcohols. So if I'm having a synthetic pathway that requires me to move from one class of an alcohol to another, it can be from a primary or from a secondary, any either case to another. Most of the times this Grignard synthesis is important. Let me give you an example by just considering that reaction that we have been given. Now this ethanol that we have used can come from ethanol, CH3, CH2, OH. But what are we going to use? From ethanol to ethanol, we are going to use a weak oxidizing agent. So I'll have that in the presence of an acid and then I heat. So in this case, you can realize that I have actually formed a full synthetic pathway. So I am moving from ethanol to propan-2-ol. So in other words, this one is a primary alcohol and this one is a secondary alcohol. You're seeing that? So whenever you're doing your organic synthesis and you're having different classes of alcohols, you can consider using the Grignard's reaction of carbonyl compounds. It can help you to do that synthesis more effectively. So that is the other one. This is part C. This is letter C, not part B, letter C. The Grignard's reaction of carbonyl compounds. Now we have posted actually, one of our admins has posted a link to our WhatsApp channel or our WhatsApp group. You can be able to find all the information that you need there. Now, in case you have any burning question that cannot wait, you can put it on the chat. I keep on checking on those chats. In case of anything, I can respond to it very fast. Make sure you attend this lesson until the end. Summarize all those reactions and we are going to use them at the end of the day. Then another reaction that can increase on the carbon chain, that was part D. This was C. Let's look at D. Now make sure you follow us on our WhatsApp channel. We also have a YouTube channel. You can follow us and all the information you need will be there. Okay, so part D, the other part, what is the reaction about? It is about how we can increase the carbon chain. So if you have not learned alcohols, it's going to be very hard for you to understand. But I believe most of you guys have done that. I've covered that up. Another one is going to be the reaction of a Grignard's reagent with carbon dioxide. Reaction of a Grignard's reagent, with carbon dioxide. With carbon dioxide. The recording is going to be enrolled is going to be put on the groups. You're going to find them there. Even after the lesson, join our groups or our channel, you'll find the recording there. The reaction of Grignard's reagent with carbon dioxide. Now, this reaction, we looked at it when we looked at the preparation of. Now, guys, let's not play with our screens. At the end of the day, the screen is going to be filled up. Please, please, please. I'm begging you, don't play with that pen-like structure on the left of your screen. The reaction of Grignard's reagent, with carbon dioxide. At the end of the lesson, the screen is going to be filled up, and we shall have nowhere to write. The reaction of Grignard's reagent with carbon dioxide. Now, in this case, we looked at this reaction. For those of you who have been with us, we looked at that reaction when we were looking at the preparation of carboxylic acids, where we have seen that we can have a Grignard's reagent, for example, CH3, CH2, Mg, MgBr. And then this Grignard's reagent can be treated with carbon dioxide, a gas, in the presence of dry ether. What are we going to form? We shall form an intermediate here, CH2, COO, Mg, Br. Then after that, we shall hydrolyze that using a dilute acid, and we shall form a carboxylic acid, CH3, CH2, COO, OOH. In that way, you're seeing that we have been able to increase on the carbon chain by one carbon atom. But where is the Grignard's reagent coming from? The Grignard's reagent is always prepared from an alkyl halide. So I'm going to have an alkyl halide of that nature. Then that is going to help me to prepare the Grignard's reagent by reacting it with magnesium in the presence of dry ether. So when you get that Grignard's reagent and you treat it with this carbon dioxide, you form that intermediate that you will later on hydrolyze with the dilute acid to form that carboxylic acid. And this carboxylic acid has opened the door to many other organic reactions. You can take it to an alcohol. From an alcohol, you can go to an alkane, to an alkene, to an alkyne, to any other reaction. For example, let me just do this on red to show you how far this reaction can go. This one, we can convert it to an alcohol by using CH3 to an alcohol of this form, CH2OH. And then we said from a carboxylic acid to an alcohol, we use what is called a reducing agent, lithium aluminium tetrahydride in the presence of dry ether. Then from here, I can move to an alkyl halide by adding PCl5. So I can go to CH3, CH2, CH2, then Cl. In other words, I have formed this alkyl halide from that alkyl halide. So the synthesis can require you to move. The question can say prepare this from this. So you're going to synthesize that to that. And that is the synthetic pathway. Because you're having an increase in the number of carbon atoms, you're going to consider steps, in other words, the reactions that are going to help you to increase the carbon chain. Somebody is saying that the difference when we are doing hydrolysis, the hydrolysis that is going to lead to the formation of a tertiary alcohol, we use aqueous ammonium chloride, and then the rest we use a dilute sulfuric acid. But the ammonium chloride is only used when we are doing the reaction of carbonyl compounds with the Grignard's reagent. So this is also one important, one rich area that you can see of how we can increase on the carbon chain. That is D. E, we are going to have the reaction of through alkynes. Through, let me add this word terminal. Through terminal alkynes. Through terminal alkynes. We can also add the carbon chain using a terminal alkyne. For example, I can have this alkyne CH3, C, triple bond, CH. And I want to increase the carbon chain by 2. The first thing that you're going to do is that you're going to add sodium in the presence of liquid ammonia. We looked at that reaction under alkynes. The only thing I'm trying to do is to bring them together so that we look at the organic chemistry as a whole, but not as separate topics. So whenever you're studying organic chemistry and you finish all the functional groups, you start looking at the organic chemistry as a single unit, but not as separate 9 topics. But you're going to bring all the 9 topics together. And what helps you to bring all the 9 topics together is organic synthesis. Another reaction is through the terminal alkynes. So I say that you're going to add sodium in the presence of liquid ammonia. And then what is going to happen? You're going to form a compound. In other words, the sodium atom is going to replace that hydrogen atom. So I'll have CH3, C, triple bond, C, then Na. Then from here, I'm going to add a Grignard's reagent of my choice, depending on the number of carbon atoms that I want to come up. For example, this one, I want 2 carbon atoms. So I add, you don't add a Grignard's reagent, sorry, but you add an alkyl halide. So I'm going to add CH3, CH2, Cl. That is the alkyl halide I've chosen to add. So what is going to happen is that the alkyl part of the alkyl halide is going to replace the sodium atom in that compound. So I'll have CH3, C, triple bond, C, CH2, CH3. And that way, you have increased the carbon chain through a terminal alkyne. A terminal alkyne is one in which the triple bond is found at the end of the compound, not in the middle like this one here. So it only works for a terminal alkyne, not this one in which the carbon to carbon triple bond is found in the middle of the compound. Is found in the middle of the compound. Now our admin is going to be helping me to respond to your questions on the chat, but make sure you're paying attention to what I'm teaching. Because the students that enrolled for the program, we are only remaining with 2 topics in organic chemistry. One of them, we are going to finish them this week of Christmas. That is amines. It's a very short one. Then the other one, we shall only need 1 lesson. That is esters. And we shall be done. Non-terminal does not work. That's why I said through the terminal alkynes. Please get me clearly. I just finished explaining that and somebody asked that question. So through the terminal alkynes. That is also one way we can increase the carbon chain. So the increase in the carbon chain comes on depending on the number of carbon atoms the alkyl halide that you're going to add is going to contain. And I believe you looked at this reaction when you were looking at the alkynes. Then after that, the last one, E, that is going to be F. F is going to be, it's called the Wurtz reaction. The Wurtz reaction. The Wurtz reaction is a reaction of alkyl halides with sodium in the presence of dry ether. So I'm going to have an alkyl halide plus sodium in the presence of dry ether. The end result is that this reaction, specifically the Wurtz reaction, doubles the carbon chain. It doubles the carbon chain. Doubles the carbon chain. So if I was having 2 carbon atoms in the alkyl halide, the final product is going to end up having 4 carbon atoms. If you're having 3, the final product is going to have 6 carbon atoms. So at the end of the day, you're going to double the carbon chain. And this reaction, you looked at it as a method of preparation of alkanes. So I believe your teachers looked at it as a method of preparation of alkanes. But for me, I'm looking at it as a method that can be used to increase the carbon chain when I am doing organic synthesis. So let me have the alkyl halide CH2, Cl, Then I'm going to add sodium in the presence of dry ether. The result is that the carbon chain is going to be doubled. So I will have an alkane that is having 4 carbon atoms, and that is the final product. So that is the Wurtz reaction. It has helped us to double the final chain. So keep on checking on the chat. All the information you need is actually available in the chat, and make sure you are available until the lesson ends, so that you don't really miss out. You don't really miss out on some of the serious things I'm going to do here. So there are about 6 reactions that I have put in place that can help us to increase on the carbon chain. So whenever you're having a synthesis that requires you to increase on the carbon chain, what you're going to do is that you're going to think about these 6 reactions, and those reactions are going to help you. Okay. Please follow us on our WhatsApp channel, BIO-CHEM Online Clinic, and all the information that you need is going to be found within that channel. Please don't miss out on vital things because of ignorance. The guys who have been with us can testify. Then after me looking at this, I'm then going to proceed and look at the reactions that reduce. This is going to be number 2. Those reactions that reduce the carbon, the reactions that decrease the carbon, the reactions that decrease the carbon chain. The first popular one that we always look at is a decarboxylation reaction of carboxylic acids. Decarboxylation of carboxylic acids. So this one here, we looked at it when we're looking at carboxylic acids. So if I'm having a carboxylic acid like this, COOH, then I treat it with soda lime, and then you heat. Usually it is going to remove the carboxyl group. So I'll end up having CH4. Or for example, you're going to have something like this. In this case, I'm having the benzene ring with this carboxyl part directly attached onto the benzene ring. So usually, if you treat that with soda lime, and then you heat, you're going to get rid of the carboxyl part. So you'll end up having that only the benzene ring. So that is the first reaction that can help us to be able to decrease on the carbon chain. Another reaction, this one here, we looked at it. For those of you who are with us, obviously by the end of December, I would have completed organic chemistry. Then the remaining time that we are going to have in January, we are going to focus so much on physical chemistry, so that we finish electrochemistry. We are remaining with only 1 lesson to finish ionic equilibrium, and then we see what happens. Then the other reaction that leads to the decrease in the carbon chain is known as Hoffmann's degradation of amines. Hoffmann's degradation of amines. It also decreases on the carbon chain by one atom. Now this one here, I'm sorry for those who have not looked at amines, but I'm going to look at this just this very Christmas week. But I can still talk about it so that the moment you look at it, you can still have it in your summary as a reaction that decreases on the carbon chain of amides. Sorry, not amines, but amides. I looked at these when I was doing carboxylic acids. It is Hoffmann's degradation of amides. So we say that amides are derivatives of carboxylic acid. So if I'm having an amine of this nature, CO, NH, NH2, that is an amide. Then you treat it with bromine in the presence of concentrated sodium hydroxide. And this reaction, you do a warming. So you warming that reaction. So the moment you make a mistake of heating, you would have failed that reaction. So in this case, you're going to reduce on the carbon chain by 1. So you're going to remove the carbon atom which is bearing the oxygen atom. So you'll end up having CH3NH, NH2. So here you have reduced on the carbon chain by one atom. And then from that amine, you can move to very many other organic compounds. For example, let me show you another example. I can have an aromatic amide like this. Like that. I want to reduce on the carbon chain by one carbon atom. So I treat that with bromine in the presence of concentrated sodium hydroxide, and then I warm. So you're going to end up having, since you're removing that, you're going to end up having an aromatic amine. That is phenylamine or aminobenzene. That is also one reaction that reduces for us the carbon chain. It's called Hoffmann's degradation of amides, and we shall look at it just this very week when we are studying the amines. That is also one reaction. Can you also use chlorine? It is only bromine. It is only bromine that works. It is only bromine that we use. So any alteration from bromine is going to cause, you're going to fail to produce the product. Why? The other ones cannot give you the result. That is why we only use bromine. If you use chlorine, it won't give you the result that you want. So why do you have to continue using it? So that is that. And also, whenever you're studying organic chemistry, try to learn how to take things the way they are. Not because to say that I am encouraging cramming, but the things we are studying were studied by people before us. So you're coming to find already a set of rules and proceedings that have already been put forward. So you just have to do that. Somebody's asking me, do they have mechanisms? I'm not here today to do mechanisms. I'm doing organic synthesis. Is that okay? Aha, it is by convention. That is actually a very good word. It is by convention. Okay. We have a lot to do. I came with a very big package that I don't know whether we are even going to finish it. Now, these people who are still playing on their screens, Mercy. There is this girl called Mercy. She's the one who has been doing it for the entire time. She has been playing with the screen, and if you're not really ready to learn, you just leave the place. Okay. Then the last reaction that can help us to reduce the carbon chain. Let me look at this part C. Is the reaction called ozonolysis. But it has a condition within which we use it for organic synthesis. So usually ozonolysis of alkenes usually yields to us normally two products. It yields to us two products. So most of the times it is not used in organic synthesis because it gives us two products depending on the position of the carbon to carbon double bond. So it gives us two products. However, in organic synthesis, it can only be used when the alkene is symmetrical. It can only be used when the alkene is symmetrical. In other words, the carbon to carbon double bond is actually located in the middle of that molecule. That is only when ozonolysis can be used to reduce the carbon chain in organic synthesis. But if you're having the alkene not being symmetrical and use ozonolysis, you're going to end up forming two different products. And those two different products won't be able to help you very well. So they won't actually make the synthesis efficient because you're going to have a mix-up of products. So what happens is that we only use an alkene that is symmetrical. That is the condition. So make sure you note that. So for example, I can have CH3, C, double bond CH, then CH, CH3. This alkene is symmetrical, and I can carry out ozonolysis to reduce on the carbon chain. The first thing that I will do, I'll react it with ozone plus zinc in the plus carbon tetrachloride. Presence of carbon tetrachloride at a temperature that is less than 20 degrees Celsius. That is going to lead to the formation of an ozonide. To lead to the formation of an ozonide, like that. Then the ozonide is going to be hydrolyzed using zinc plus water in the presence of ethanoic acid. This is number 2. So you end up forming that. You end up forming an aldehyde. So the ozonolysis of a symmetrical alkane leads to the formation of a single product. This product is a single product, and that is why we recommend it to be used in synthesis only when the alkene is symmetrical. But when you're having an alkene that is not symmetrical, you're going to have a mix-up of products, and that is going to make your synthesis very, very inefficient. So those are the reactions that can help you to master the changes in carbon content as you're doing your organic synthesis. The reactions that increase on the carbon chain and the reactions that decrease on the carbon chain. So depending on the final and the initial products, you can use any of those reactions within the steps of the synthesis that you have to find the final product. So that is the first wisdom that you need in organic synthesis. I hope that is okay. So I hope you people have summarized those reactions very well. Why? Because if you're left alone to summarize them, it's going to become a little bit very, very hard. So that's why I have summarized them for you. So we have looked at the reaction that increase on the carbon chain. We have looked at the reactions that decrease on the carbon chain. Then we are going to look at the reactions that involve oxidizing agents and reducing agents. That is the next set of reactions we are going to look at. The oxidizing agents and the reducing agents. When you also know those reactions, they are very common in organic synthesis. And when you know them, it's going to become very easy for you to carry out synthesis. So let me look at the ones that involve oxidizing agents and reducing agents. I organized about 30 synthesis to do, but the aspect of time may not be on our side. Time may not be on our side, but I had compiled those questions, and by the time we would finish doing those questions, you would realize that organic synthesis would be very easy for you. The mechanisms of reactions are normally obvious, and as you keep on doing organic chemistry, you're going to realize that mechanisms are going to become very obvious. What requires the manipulation is normally the synthesis, is where the manipulation comes about. So this is number 3, the reactions that involve the use of reducing agents. You have to know them. And I'm going to summarize all of them as far as the scope of your syllabus. The most important, as far as the scope of your syllabus is. So the first one here is when you're reducing aldehydes to primary alcohols. I remember telling you, Paul, that we can have primary alcohols. Let me just summarize it here. You can have a primary alcohol. Then you're going to have an aldehyde. And then you're going to have a carboxylic acid. Let me just use this, a very this small summary to help you guys. Now, when I'm moving from a primary alcohol directly to a carboxylic acid, you normally use oxidizing agents. We normally use oxidizing agent. But as I'm moving from a primary alcohol to an aldehyde, what we do, we use a weak oxidizing agent, something like that. Then we hit. So this one here is a weak oxidizing agent. Then from an aldehyde to a carboxylic acid, you can still use an oxidizing agent. So you can use an oxidizing agent. Then from a primary alcohol still up to a carboxylic acid, you can still use an oxidizing agent, but the difference here is that you're going to use a strong oxidizing agent. You're going to use a strong oxidizing agent. So when you're moving forward in that direction, it's going to require you to use oxidizing agents. But where are you going to use the reducing agents from? The reducing agents are going to be used when you're moving backwards. So let me represent them with a yellow arrow. So this yellow arrow, let me say reducing agent. The first place you're going to use a reducing agent is when you're moving from an aldehyde to a primary alcohol. So that is 1. An aldehyde to a primary alcohol. And then when you're also moving, that is the first scheme I gave you. Let me first draw the second scheme. You can have a secondary alcohol. Let me draw both schemes. You can have a secondary alcohol. These ones are oxidized directly into, they are oxidized into ketones, and their oxidation does not proceed into a carboxylic acid. So when I'm moving from a secondary alcohol to a ketone, what I do is that I use an oxidizing agent. But when I am moving from a ketone to a secondary alcohol, I use a reducing agent. And most of the time, the reducing agent we use is lithium aluminium tetrahydride. Lithium aluminium tetrahydride in the presence of dry ether. Aha. So use an oxidizing agent. Then from a ketone back to an alcohol, you use a reducing agent. Then from a carboxylic acid back to an alcohol, I'm using yellow for the reducing agents. From a carboxylic acid back to an alcohol, you also use a reducing agent. So when you look at that scheme, it can help you summarize where you need to use the reducing agents from. Now I'm just going to make a summary here. When I'm moving from aldehydes to primary, I hope all of us know the meaning of that. We have used that in O level to mean primary producers, all those things. Primary alcohol. Then from ketones straight up to secondary alcohols. Then from a carboxylic acid from a carboxylic acid up to a primary alcohol. Now, all these reactions involve the use of reducing agents. I've already talked about the oxidizing agents, whereby you're having the forward reaction from a primary alcohol to an aldehyde. Now, let me just combine this together, reducing agents and the oxidizing agents. Reducing agents and oxidizing agents. So in that case, when you're having from a primary alcohol to an aldehyde, you use a weak oxidizing agent. So here I've put that point that from this point, the oxidizing agent has to be weak. Then from an aldehyde to a carboxylic acid, you can use any oxidizing agent. Then from a primary alcohol straight up to a carboxylic acid, you use a strong oxidizing agent. Then one area that we can also use an oxidizing agent is when I'm having an amide to an amine. For example, so this one here is from. We are going to look at this under amines. That is this very weak. From an amide to an amine, I will use a reducing agent. For example, look at that amide CH3CONH2. In this case, I use the reducing agent lithium aluminium tetrahydride in the presence of dry ether. In the presence of dry ether. In that case, you're not going to reduce the carbon chain, but you're going to reduce it by removing obviously the oxygen atom. So I'll have CH3, CH2, NH2. You can also have this amide, an aromatic amide. Then you can reduce that with lithium, aluminium tetrahydride in the presence of dry ether. Compared to Hoffmann's degradation, we do not reduce on the carbon chain. So you'll have the carbon chain remaining constant. CH2, NH2. And you have had, and you can see that reduction reaction. Then another oxidation. So these are all the reduction reactions. Then the last oxidation reaction that is unique from the one of the alcohols. The last oxidation reaction is whereby you're going to oxidize methyl benzene to benzaldehyde. So from methyl benzene, this one we looked at it when we were looking at the reactions of methyl benzene, and we looked at it under the preparation of carbonyl compounds. What I'm doing is that I'm trying to put them together such that we consider the organic chemistry as a whole, but not as segments. So this one here can lead to the preparation of benzaldehyde using a weak oxidizing agent. That is oxidation. Then another one I'd actually forgotten. This is one. Then two, you can have alkenes being oxidized to diols. Alkenes being oxidized to diols. For example, I can have this CH2, C, then CH2. You're going to use an oxidizing agent in the presence of an alkaline medium. So I'll have a strong oxidizing agent there. Instead of us doing it in acidic medium, I'm going to do it in alkaline medium. And then there is not going to be heating that is going to be required. So at the end of the day, I'll have a diol now. So you're going to have the hydroxyl groups adding themselves across the carbon-oxygen double bond. And this is going to lead to the formation of a diol. So those are the oxidation, and the reduction reactions. You should be in position to know the oxidizing agents. Know all the oxidizing agents that we have, a few of them that can help you. Oxidizing agents. Which oxidizing agents do we have? You should be able to classify them into strong oxidizing agents These are the strong oxidizing agents. Then we can have the weak oxidizing agents. This is manganese 4 oxide. Then you can have chromium 6 oxide. All of them are in the presence of an acid. And when you're doing the reaction, in both cases, you heat. So these are weak oxidizing agents. So those are the few oxidizing agents you should know. Then the reducing agent that is used commonly is lithium aluminium tetrahydride. So those are the reactions that involve oxidation and reduction. You should be in position to know them very well. You should be in position to know them very well. By 10:30, this lesson should be done, but I'm going to the most important part. We may not be in position to look at those questions, only that I may have to put the next Sunday, we are still going to have organic synthesis. So I'm going to put organic synthesis season 2 to answer now the questions. But now here I'm giving the general concepts that you need when you're doing organic synthesis. So you're going to see how the organic synthesis we are going to do are going to have very many of these things. So no oxidation and reduction reactions. How you're moving from the alcohols to the carbonyl compounds to the carboxylic acids, and then how you're moving backwards. And then the few special people playing around with our screen, please help us and allow us to learn. So we are still looking at the secret weapon. And I say the first secret weapon is the reaction that increase on the carbon chain. The second secret weapon is the reaction that decrease on the carbon chain. The third secret weapon is the reaction that involve Vivian. Vivian, please remove that. Vivian, remove that. You people. I don't know how you people are really. The second, we have looked at the first secret weapon, the reactions that increase on the carbon chain. The second weapon, the reactions that decrease on the carbon chain. The third weapon, the reactions that involve reducing agents, oxidizing agents. Then I'm going to look at this number 5. It's the biggest. The reactions that involve manipulation of the substituent groups on the benzene ring. Then these ones that involve specific temperature conditions, you just, I will summarize them but later. But I'm going to dwell a lot on the reactions that involve the manipulation of the substituent groups on the benzene ring. Now our phone numbers are in the chat. One of our admins is putting them there. You can contact us after this to make sure that you stay posted and you enroll in our program. Follow us on WhatsApp in our WhatsApp channel, BIO-CHEM Online Clinic. Follow us on YouTube in BIO-CHEM Online Store. Then you can join our various WhatsApp platforms. So we are going to look at the manipulation of the substituent groups on the benzene ring. So this one is going to be, you guys are going to love it. I've actually made a summary about that, and I've made a summary that shows all the substituent groups on the benzene ring and how they can be and how they are manipulated. So the last one we are looking at is, because I know now most people, their data is almost getting done. So that's why I'm also summarizing, because the moment somebody's data gets done, I don't think they can have the energy to buy more data. So manipulation on the benzene ring. This is one tactic you should be able to know in organic synthesis. Manipulation on the benzene ring. manipulation on the benzene ring. Now, how do we manipulate on the benzene ring? Now, I'm going to do almost all the reactions that I can remember on the manipulation on the benzene ring. Then after that, I am going to share with you the written work that I'm just going to write down some work on the manipulation on the benzene ring. So I'm just going to do a summary and I'm going to show you how we can manipulate the reactions on the benzene ring. Manipulation on the benzene ring. So I'm having a benzene ring at the center here. Let me write the benzene ring at the center there. Now, when you were studying benzene, you looked at the electrophilic substitution reactions on the benzene ring. Obviously, you talked about all those things that I don't want to go into, but I'm just going to look at the reactions. The first reaction that you looked at was sulfonation, isn't it? So you looked at sulfonation, where you could be able to prepare benzene sulfonic acid from benzene. So which condition do you use? The condition is going to be fuming sulfuric acid, and then you warm. That was one of the electrophilic substitution reactions you looked at in the benzene ring. The next one you're going to look at is halogenation on the benzene ring, whereby you're going to add. Now I'm going to start this and the thing is going to grow into a bigger kind of synthesis that is almost going to cover 2 pages. Just hold on and see how it's going to come. Then another one is going to be you're adding, let me assume you're doing bromobenzene. So you're having that. For you to get bromobenzene, you add a halogen, that is bromine, in the presence of a halogen carrier, aluminium bromide. Then after looking at that, you also did nitration. You can also have nitration there, whereby you're adding the nitronium ion onto the benzene ring, substituting, sorry. So you're going to form nitrobenzene. But to form nitrobenzene, what happened? We used concentrated. Please, those people writing on our screen, please forgive us. We are about to complete. If the lesson is itching you, we are almost done. Conc nitric acid, and then conc sulfuric acid, and then you heat between 55 to 60 degrees Celsius. Then after the nitrobenzene, we looked at alkylation. In other words, how to add an alkyl group on the benzene ring. So you can add an alkyl group there. Let me assume I'm doing methyl benzene. So for me to add the methyl group there, I use an alkyl halide CH3Cl in the presence of a halogen carrier. Then after that, you can look at, I think that is done. Let me look at the chlorination also. Assume I'm adding chlorine. Here, what are the conditions? The condition is that we use chlorine in the presence of the halogen carrier. Now, that is the baseline that you're supposed to first know when you're manipulating the benzene ring. You're supposed to be in position to know the reactions that are going to form a single substituent group onto the benzene ring. And these are the major reactions. All of the other compounds that are going to be formed from the benzene ring are going to be as a result of changing these other substituent groups that are formed on the benzene ring. But before that, let me consider something important. There is one reaction, it's called a polymerization reaction of ethine, whereby you're having ethine. I'm having ethine here, and ethine is being converted to benzene. Now, this reaction is very important. Why? Because you see, ethine is actually a straight chain compound. It's an aliphatic compound. Then benzene is an aromatic compound. Now, this reaction helps us to connect the aromatic world to the aliphatic world. So in that, what are the conditions? You can use organonickel catalyst. organonickel catalyst at the temperature of 60 degrees Celsius. That is how you can produce benzene from ethane. There are very many other ways, but this one here is very important. So that is the first step when you're doing the manipulations on the benzene ring. You should be in position to build these 1, 2, 3, 4, 5 compounds from that benzene ring. Then we are going to start looking at the other compounds. Now you're going to watch how the chemistry is going to increase. Now from methyl benzene, you can look at other things. For example, from methyl benzene, I can form benzaldehyde. For methyl benzene, I can be in position to form benzaldehyde by using a weak oxidizing agent. So I can use maybe manganese 4 oxide in the presence of an acid, and then I heat. Then I can use still a strong oxidizing agent from this methyl benzene, and it's going to give me a carboxylic acid. So in this case, I can use a strong oxidizing agent, the manganate 7 ions, and then I heat. So in this case, you're going to form ethanoic acid. From ethanoic acid, you can look at the reactions of ethanoic acid. First and foremost, we can lead to those reactions that form for us the derivatives of carboxylic acids. So I'll first form an amide like that. How do you form an amide? I use ammonium carbonate, solid, then you heat at 100 degrees Celsius. Then that amide, you can still look at from this benzene ring, you can form an acid anhydride from the carboxylic acid. Remember, we said that it is part of the derivatives of the carboxylic acids. I can form this acid anhydride, COCl, by using what? PCl5. And after forming that acid anhydride, this carboxylic acid can still be converted back to the benzene ring. I hope you know that. We saw the decarboxylation reaction, where you're having soda lime, and then you heat. You can convert back that carboxylic acid back to the benzene ring. Then from there, from this amide that we have formed, we can do two things. We can do a Hoffmann's degradation that is going to remove the carbon atom, one carbon atom, so that we form amino benzene. In this case, this one is going to require us to use bromine, then conc sodium hydroxide, and then you warm. That reaction has reduced for us the carbon chain by one carbon atom. Or you can decide to just use a reducing agent like what we looked at by you using lithium aluminium tetrahydride in the presence of dry ether. In this case, you would just form amino benzene. So those are the routes that are emerging from methyl benzene, leading to the formation of the carboxylic acids, and then all the derivatives of the carboxylic acids. Then from here, this methyl benzene, it is going to lead us into all the other reactions of the carbonyl compounds. It's going to lead you to all the other reactions of carbonyl compounds. That is what benzaldehyde is going to lead to. So there you can perform the reaction with hydrazines, with hydrazones, with hydroxylamines. You're seeing that all those kinds of things, and you'll have other products that are coming from benzaldehyde. That is the first route. Then when you look at this nitrobenzene, it's also very rich in that it can give rise to aminobenzene also. This one can give rise to aminobenzene. But how does this produce aminobenzene? The condition is that you're going to use tin in the presence of solid tin, in the presence of concentrated sodium hydroxide, and then you're going to heat. That is going to lead to the formation of aminobenzene. After you forming aminobenzene, you can go ahead and form benzene diazonium salt. You can go ahead and form a benzene diazonium salt that is of that nature. How do you form a benzene diazonium salt? Sorry, I think I made a small mistake. When you're moving from nitrobenzene to aminobenzene, you actually use sodium nitrite. Sorry for that error. You're going to use sodium nitrite. Sodium nitrite in the presence of concentrated hydrochloric acid at 0 degrees Celsius. Then you're going to form aminobenzene. From aminobenzene, you can form for us benzene diazonium salt by using tin in the presence of what? The presence of concentrated hydrochloric acid, then you heat. That is going to lead to the formation of benzene diazonium salt. Now, benzene diazonium salt is very important in organic synthesis. Let me circle it with blue. Why? From benzene diazonium salt, we can lead to the formation of very many other compounds. Let me just sample a few. From benzene diazonium salt, you can have the coupling reactions of phenol. So benzene diazonium salt can react with phenol in the presence of an alkaline to produce the dyes that we looked at when we studied phenol. Then this benzene diazonium salt can be converted to phenol. It can be converted to phenol by treating it with what? With water, isn't so? And then you warm at which temperature? At 50 degrees Celsius. This benzene diazonium salt can be converted to that compound. You're going to have, by treating it with potassium cyanide in the presence of copper 1 cyanide, and then you warm. Obviously, this one here, we looked at it as a reaction that can also increase the carbon chain. So there we add acidified water and we reflux. Acidified water and then you reflux. That reaction is going to give us a carboxylic acid. This same benzene diazonium salt can give us, let me just wrap it up. It can give us that halogen. It can give us that. It can give us this. It can also give us bromine. By the way, these ones are formed as similar. For chlorine, you will have copper 2, copper 1 chloride in the presence of concentrated hydrochloric acid, and then you warm. For bromobenzene, you're going to have the same thing, but you're going to just change the chlorine to bromine. Then this same benzene diazonium salt can lead to the formation of iodobenzene. Now, the only way iodobenzene can be formed is from benzene diazonium salt. How do you do it? By using potassium iodide, and then you warm. So that is the second part of the manipulation. From nitrobenzene, you can have aminobenzene coming in, and then aminobenzene gives you benzene diazonium salt that connects to very many other organic compounds there. So the manipulation is actually endless. In other words, aminobenzene can still give you this compound. If I told them to add bromine water into aminobenzene, it can give me that compound. Br. That is 2,4,5-tribromo-phenylamine. 2,4,5-tribromo-phenylamine. That is the compound. So the conversions are very endless. Then when we looked at the preparation of methylbenzene, we say that methylbenzene can be prepared from bromobenzene using Fittig's reaction. So here I have you can have methyl, sorry, not methyl, but chloroethane in the presence of sodium and then dry ether. And then you're going to form that that methyl benzene. And then you're going to have other reactions unfolding from that. Then from this benzene sulfonic acid, it can lead to the formation of phenol. How can you form phenol from that? You can first use sodium hydroxide. You hydrolyze that using sodium hydroxide to form that. Then from here, you can end up, you can end up forming this a sodium, this phenoxide ion. But how is that formed? That is going to be formed by using sodium hydroxide, and then you reflux. Then after you hydrolyze the product to form for us phenol. Obviously using a dilute acid. Now this reaction, you looked at it when you're looking at the preparation of phenol. So phenol can also be prepared from that pathway. Then this chlorobenzene can also prepare for us phenol. We say that this one can go directly into the sodium phenoxide. How are you going to do that? Using sodium hydroxide, at which temperature? 360 degrees Celsius and 150 atmospheres of pressure. Then after you hydrolyze this using a dilute acid, HCl, and you'd be in position to form phenol. Then from phenol, you can go back to aliphatic compounds. You can remove the benzene ring by performing an addition reaction of phenol, whereby you're going to add hydrogen in the presence of nickel catalyst, and then you heat at 200 degrees Celsius. So I'll have that. So you're going to remove the pi electrons of the benzene ring. So you're going to have that. Then from here, I can treat this by, now this one here is now an alcohol. From phenol, you have moved to the alcohol. You looked at all these reactions. I'm just showing you the manipulation. Then from there, I can remove that by treating it with concentrated sulfuric acid at 180 degrees Celsius. So I'll end up forming an alkene. Then from here, you can move into form very many compounds. And this one here, you're going to follow addition reactions of alkenes. You're going to follow the addition reaction of alkenes. For example, you can add hydrogen bromide, you can add a halogen, you can do ozonolysis, you can do very many things by that reaction. Then from phenol, you can go and look at the other types of reaction that phenol can undergo. So from phenol here, you can form in case you add bromine to phenol, what is going to happen? You're going to form a product which was similar when we added bromine to aminobenzene. You're going to have that and that. That is one compound. Or you can have you can add zinc dust. You can add zinc dust on phenol, and then you're going to form the benzene ring. Zinc dust, and then you heat. You'll form benzene. Then after that, still on phenol, you can add you can go and look at the side chain reactions of phenol. You look at the side chain reactions. For example, the formation of esters. Phenol can be in position to form for us an ester. So you look at that. So I'll have O, C, O, maybe CH, CH3. Phenol can be in position to form for us ethers by having that reaction. O, CH2, CH, CH3. That is Williamson's synthesis, whereby you're going to have CH3, you're going to add an alkyl halide, CH2, in the presence of a halogen, then obviously in an alkaline medium. Here you're going to add an acid chloride, CH3, CH2, COCl, and still in the presence of an alkaline, of an alkali. And then you go and look at all those side chain reactions of phenol. Then obviously from bromobenzene, why is bromobenzene? Let me start another one a little bit here. We say that we could be able to form this bromobenzene. From bromobenzene, we can form a Grignard's reagent from here by adding magnesium in the presence of dry ether. In that case, you will have then after that is a Grignard's reagent, and you're going to continue to produce for us a carboxylic acid. Because of space, I may not be able to write it. And the manipulation is very diverse. But what I want to say is that the most important thing is that when you're doing the manipulations on the benzene ring, the first thing is that I'm going to highlight what you actually need. The first thing is that from the benzene ring here, sorry, from the benzene ring there, you can move into the compounds the components that can be formed from the benzene ring by electrophilic substitution. And then the other reactions that are coming are going to be as an effect of that group that you have attached on the benzene ring. That is that. Then so that is how you handle the orientation. In other words, the substituent groups that can be attached onto the benzene ring. So that is how you handle those syntheses. So you go and make sure you practice a lot of those things, and at the end of the day, you'll be able to come up with a bigger kind of tree diagram for yourself. Normally, for me, I could use that size of a paper of an art book, and I fill all of it with all the reactions that are involving the side chain, the substituent groups on the benzene ring. Our time is far much spent, and but if you have not yet joined any of our WhatsApp platforms, because most of the information that we have concerning our programs is put in those WhatsApp platforms. The link has been shared into the group. Maybe admin desire you send it again. Now, those of you playing around with the screen, people, I don't know what is wrong with people. It looks like people are rioting. I don't know, but so those are the secret weapons that I can give you for now on synthesis. The next time we shall meet, I'm going to look at the concept of inductive orientation on the benzene ring. How that the presence of other substituent groups on the benzene ring can affect the position within which the other substituent groups can also be attached onto the benzene ring. So there are these people who are now playing with the screen because the lesson is done. But anyway, it's okay. But next week, I'm going to post the links for this week tomorrow morning. I'm going to do that, and we shall see what happens. So I think because of that, we can say I can wish you guys a good night. I can wish you guys a good night, and thank you so much for attending. For those of you that have not yet enrolled for our program, for our holiday program, make sure that you contact those numbers that were given on the chat. And join our WhatsApp groups because I'll be in position to share most of the information that you need to make sure that you are in sync with us on the WhatsApp platforms. Thank you for being patient. Thank you for listening, and I wish you guys the best. The phone numbers are there on the chat. Please copy them up before I close. Copy those phone numbers. You can inbox us after, and then we make sure we add you in the groups and we keep you posted on whatever program that we have for you to make sure that you are academically sound. Now this Gurindwa Paul. Now for this question here, contact admin Desire after the lesson. He will help you. For me, I'm already tired now. So admin Desire will respond to your other questions that you have. But I think with that, have a good night. You can follow our WhatsApp channel, and the links are there in the chat.